I'm gonna the first part of this presentation is
on both sides, and you got what a
sorry. Someone say something?
No,
They
you're
just
good.
got unmuted.
Yeah.
So the first part of this presentation, some of you may have seen at the Hungry Canyons meeting back on November 22nd, where I'm just going to cover some basic geology kind of stuff regarding Southwest Iowa, and then I'm going to get more into detail about what kind of gullies you can find in Southwest Iowa, where you're going to find them, and what you can do to prevent them or control them. And then Terry Gleaves is going to talk a little bit about potential NRCS cost share. And if Brian Holmes is still around, he might want to talk about whatever he wants to cover as far as what I've missed. Try to throw you under the bus like that, Brian, but you're the best at this, so well, I'll just I'll go ahead and start then. Oops. You guys, there we go. Okay. So Iowa it started out as a prairie state. This is a land cover map from the 1850s. And this one here is a land cover map from the 1850s. It shows that most of Iowa was prairie, and there was forests along our river corridors. This is a 2002 satellite land cover for Iowa, and you can see that most of the prairie has become cropland. We do have some grassland in the light green, and there is still some forest area along the river valleys. But for the most part, the landscape of the land use of Iowa has dramatically changed. Oh, it's not going to let me do this. Hold on. Okay. Why? Had the same trouble I had at that meeting on the 22nd. The screen I want to share it on is this one.
Recording in progress.
Just have to go the old-fashioned way. Just kind of, you're going to see everything all at once rather than kind of phase it in. So to get the landscape of Iowa so that it is predominantly ag use, we had to change how water left the landscape. So here's a photo from 1914 of tile being dug by hand on the Des Moines lobe. Here's a photo of a steam dredge that's working down some fairly decent sized river in 1910. So the major periods of this drainage development happened in the early the 1870s through the 1920s, and then there was a second push in the 45 through 60. Most of our stream channels were straightened in western Iowa between probably, I would say, maybe 1900 through 1950. And here is a the landform map of the landform regions of Iowa, and pretty much all around the state you had some kind of alterations to the hydraulic system or hydrologic system. In the Des Moines lobe and the Northwest Plains, Iowan surface, when you channelized a stream or put a stream into tile, it didn't have as much of an impact because the soil is tighter, and just things didn't erode like they did in the Less Hills in the southern Iowa Drift Plain. So one of the main reasons for that is because this area of Iowa in the Green and the Less Hills is covered by loess. And loess is this windblown silt deposit that's formed downwind from large river valleys around the world. There's a really big deposit in China. But one of the biggest is here the second biggest is here in the mid-continent region of North America. And this loess was blown across the Midwest from the glaciers that were sitting over the northern plains. And so during the summer, you had these glaciers in North Dakota, South Dakota, Minnesota. These things were melting. Water was flowing down this ancestral Missouri River Valley, and the floodplain was covered. And so there wasn't any dust or anything moving. But in the winter, when these glaciers were not melting, they were accumulating snow, the flow basically stopped. There wasn't anything to keep the water going. And so this wide floodplain especially between Iowa and Nebraska, the old Missouri or the Missouri River Valley was exposed. So think from like Missouri Valley over to Blair, or eastern Council Bluffs over to Omaha, or Ottawa. Well, it'd even be further than Ottawa, like Soldier all the way over to Decatur. Just this huge valley, sometimes up to 15 miles wide, was just completely barren. It had water on it in the summer. Now there's nothing there anymore. And, we always get west winds. And so the winds would pick up the silt that was laying on this wide open expanse of floodplain and pick it up and take it across Iowa. The thickest deposits of that silt, as it was picked up and moved and then dropped by the wind, was thickest here in western Iowa, nearest the source. And this area near the Missouri River also has the largest particle size, so almost like a sand-sized grain. Whereas farther from the source, let's say Muscatine or even Davenport, the loess thins out to maybe 4 feet thick maximum. And by the time it gets all the way over there, the loess is really small particles. And so this loess completely covered the pre-existing landscape here especially in southern, southwestern Iowa. As you get further east, the pre-existing landscape becomes exposed sometimes. But especially here in southwest Iowa, bedrock is buried extremely deep. And, there's a ancestral Missouri River channel that flows basically along the path of the West Nishnabotna River up all the way through Denison. And this valley goes through Denison, Harlan, and on south. It's up to 200 feet. If you dig on the surface, it's up to 200 feet before you get to any bedrock. And it's just filled with, glacial deposits and this loess. But there are a few bedrock highs around southwest Iowa. There's one kind of by Lewis. There's one by Logan. The Tarkio River Valley has incised so much that it's actually encountered the bedrock. So there's several bedrock ledges in the Tarkio River bottom. But back to this loess. So this loess form these basically really large dunes in western Iowa, and the first several miles once you get off the Missouri River floodplain is what we would call the loess hills proper. Those deposits tend to be about 200 feet thick of just loess. And these dunes have been eroded to form this really sharp knife-edged ridges, and they have these narrow alluvium-filled valleys with steep slide slopes. And in these valleys, you'll have gullies with large vertical head cuts in them. And I'll get back to that because that's kind of the whole purpose of the talk. But another thing that's really cool about loess is that loess here in western Iowa has, we use a lot of terraces because of the loess soil to help, because we have these steep hill slopes. The terraces slow down the water as it's moving off the landscape. And in the loess hills proper, that first, I don't know, maybe 5 to 15 miles closest to the Missouri River bottom, we don't need to tile our terraces because the loess hills have this really high vertical permeability. So basically water that lands on the surface can move down through the soil column because it has this high vertical permeability. And the reason for that is because the particles of the loess is a larger particle. It's like a sand. And the paleosols are really deep. And so a paleosol is basically a buried soil. So you can think of like if you dig into a soil and you find most developed soils will have a B horizon. And that's where a lot of clays have been moved down through the soil horizon by water infiltrating into the soil, and it carries with it clay. And if you have an old paleosol, that can prevent water from moving downward. But because we have so much loess, and it happens so quickly, we don't have many paleosols, and if we do, they're buried pretty deep. So terraces near the loess hills don't need tile, whereas terraces in the what I would call the deep loess, so basically beyond 15 miles away from the Missouri River bottom, might need tile because they have reduced vertical permeability. Basically, the soil particles are larger, there's more clay content, and the paleosols can be closer to the surface. So if you hit a paleosol, you're going to have a perch water table, which means you're going to have water basically pouring out of this or seeping out of the side hill. So this loess here in western Iowa is it's highly erodible, especially when it's exposed in a stream bed. And the thicker the loess deposit is, the greater the potential for erosion. And all these Missouri River Valley loess deposits that reach a great enough depth of basically 5 meters, which would be like, 15 feet or greater, you can have widespread channel downcutting and erosion. So here is a photo of Walnut Creek. It's probably a 25, 30-year-old photo now. But this is Walnut Creek. This is Highway 6. This is M47 going up to Walnut. And this is the old channel that was, I think it was channelized in around 1945. So this old channel is, I don't know, maybe 5 feet deep, 20 feet wide, whereas this new channel is 150 feet wide and maybe 15 to 20 feet deep. When they channelized this, I actually have cross sections. They created a trapezoidal channel, made it the bottom 12 foot, or was it 12-foot bottom, I think, with like 8-foot banks. And so basically the channel has just eroded out a much, much larger channel than what we engineered for it back in the 40s. And that was because the stream is straightened. And so when you can see this old channel, you think about that just kind of meandering all over the landscape, and then we make this straight line. Well, if you take a piece of string and you make squiggles in it and then straighten it out, you're going to see that you've got your string will cover a larger area when you straighten it out. But per stream length, I guess, the slope is going to be steeper. So we removed about half of the channel length from the original Walnut Creek when we straightened this channel. So that means the channel is now twice as steep as it used to be. And if we had tills or bedrock, straightening the stream and making it twice as steep might not be a terrible thing. But here in Western Iowa, we have these loess soils. It caused the stream to downcut and widen. And now we have, really high sediment loads coming from our watersheds here in Western Iowa. So take all this information, we can kind of get a history of what's happened here in Western Iowa as far as our streams. And so people started settling in our area of Southwest Iowa between the mid 1850s and the early 1900s, and they started doing heavy ag. Basically turned almost every acre of land into some kind of production. But back then we didn't have soil conservation techniques. And so this caused a massive amount of erosion from the fields and uplands because we have these steep side slopes. And so these channels here in Western Iowa became filled with eroded sediment, which then started to cause flooding, reduced conveyance, which is the movement of water through during a flood, and increased the duration of floods. And so people decided, well, we can't have this. We don't want more flooding, so we're going to dredge the streams and straighten them to improve land drainage and reduce flooding, which has occurred. We don't flood nearly as often as most other places in Iowa because our channels are so deep. There are some channels in Western Iowa that I don't think have flooded since the 40s. And so this channelization did reduce flooding, but it also caused this downcutting and widening. And as sediment moves in from upstream, as further as erosion moves its way upstream and sends the sediment downstream, these downstream sections will fill in, and a new meandering channel will form in this deeper incised channel. And what's, I think, really important here to know is that here in Southwest Iowa, 75 to 80% of the soil that's moving through our water systems isn't because of erosion from farming on the landscape, but it's because of bank erosion and gully head cuts. So now I'm kind of done with all the text slides, and I'll just show you a lot of pictures from here on out. So here's some photos of what nick points look like. So a nick point is where the stream is deepening. It's basically a waterfall. And that waterfall will move upstream over time. Niagara Falls is a really big nick point that moves pretty slowly because it's moving through bedrock. All of our channels here in Iowa western Iowa are basically silt. And so these nick points can move pretty rapidly. And they tend to have a surface expression on the upstream side and then a big scour hole on the downstream side. And this nick point, for example, on Walnut Creek in Montgomery County, north of Red Oak, this is about 8 to 10 foot deep in the scour hole, whereas the nick point itself is maybe only about 6 inches high above the water surface. Here's a nick point moving off of Silver Creek, and it's forming 2 different waterfalls, and it's moving its way upstream. So here's another nick point. As this nick point passes, or series of nick points pass, the stream bed is scoured out because of that scour hole, and the bank will slide into the eroded bottom. There's just nothing to hold up those banks anymore, and so erosion can more easily take those bank deposits away. And it's important to note that we can have buffers are a good thing, but buffers won't stop stream bank erosion, because if the bed is unstable, the bank is also going to be unstable. Basically the toe of the bank is the critical factor. If the toe of the bank is stable, it's not going to go anywhere, and the material above the toe is not going to go anywhere. But if the bed is unstable, that means the toe is unstable, and then the bank's going to slide. Here's a big slide here up in Monona County. And so as you move up in the stream system, as those streams downcut, all of the tributaries have to adjust to this new base level. So now they're going to erode down to this new elevation. And especially if you're in the Luss Hills, you're going to find really large gullies. And a gully head cut is basically just this bowl-shaped area at the top. So here's the waterway would be coming in here, and as the water falls over, it's just eroding this head, and the head cut's moving upstream, and the banks slide into the eroded area. Here's another head cut moving up this valley. This picture here is in Fremont. This one's in Mills. This one's in Potawatomi. And you're going to have really, really deep gullies in the Luss Hills, like I was saying. This is in Mills County in the Bunsey Creek watershed. That's Brian Holmes for scale. That's Brian Holmes's head, the little red hat he's got on. This is Kevin Sievers, and then I'm down further into the gully. And this is a a large soil bridge or soil pipe. And so it just eroded right through it. This is about a 50-foot drop. And these gullies, like I was saying, can grow really rapidly. Here's some corn rows from the previous year, and the gullies just eroded right through it. Here's look at this NRCS state text name. This is Cass County. This is taken about 20 years ago. Back in Mills County in the Loess Hills, here this first fence was about 5 years ago. And the landowner has cattle, and he's trying to prevent the cattle from falling off the cliff and dying. And so he keeps moving his fence. So this is the fence 5 years ago. This is the fence from a year ago. And he's already seeing erosion. I would say there's 4 different main types of gullies. There's a nick point that happens inside an already incised channel. There's what I would call a classic gully head cut. And again, this is this bowl shape with the land surface fairly level, and water is just coming off the landscape through waterways, or doesn't have to be flat, but it can be steep ground, but it just cascades over this vertical drop, and this head cut will continue to march upstream. Another one would be what I call a cutback. So along river valleys, or along river channels or stream channels, you're going to have, it's been incising now for almost 100 years, and you're going to have these gullies working off of the stream channel into basically flatland or old floodplain around it, around the stream channel. And then you're going to have what I would call discontinuous gullies. And they're tend to be up on the landscape. A nick point normally can be solved by some kind of in-stream structure like a weir or a drop spillway. Discontinuous gullies can normally be solved by either a sediment basin or a terrace. Cutbacks and classic gullies are normally solved with some kind of combination of either retention structure or a full flow structure, and I'll show examples of all those. So here's a map of the Silver Creek watershed. I did this analysis probably 10 years ago or so, and I just labeled all the different types of gullies, gave them each a distinct symbol. So there's the in-channel nick points, the classic head cuts, the cutbacks off of streams, and then culverts or fence lines. On a lot of the time you'll see erosion move up and hit something, and then it can't move past it. So you see that a lot at either culvert outlets or fence lines, and then these discontinuous gullies. And so again, you normally can take care of the discontinuous gullies with terraces, but these cutbacks normally are going to be probably a full flow structure down in the valley, and the classic head cuts are going to tend to be like a kind of a water retention structure further up in the landscape. So this is Silver Creek. This is what it looks like if you're in the Loess Hills. This is Wabunsee Creek. This is a large PO 566 structure downstream, and you can just see all these gully head cuts. So for scale here, this, the valley here is probably, maybe 100 feet deep, and your biggest drops are going to be 8 to 10 feet in Silver Creek. In Wabunsee watershed, you have a scale of probably a relief of probably about 200 feet, and your biggest drops are going to be close to 70 feet. Again, because this is that loess. It has the sand particles. It has a lot of infiltration, and also it has the steepest slope to get to the Missouri River. Whereas this one, water has to flow down the Silver Creek, and then go into the Nishnabotna, then go into the Missouri. Whereas this one goes directly from Wabunsee Creek right into the Missouri. So it's a steeper gradient on the hill slopes. So basically, the way to prevent this erosion from moving upstream is to stabilize the stream bed. And this is different than how a lot of conservation methods work. Typically, they start in the upland and work and are preventing water from moving downstream. Well, stream degradation works its way from downstream to upstream. And so you're wanting to stop those nick points or head cuts from moving up the watershed. And so you need to have structures at regular intervals if you're going to stop them. And Western Iowa has the greatest concentration of grade control structures probably anywhere in the world. And that's because we have these lush soils, these highly altered stream system, high drainage density, a high road density, and then a high agricultural land use density. So I'm just going to finish up the presentation here showing several different types of on-farm grade control structures landowners can do. There are mainly 5 different types. So you can do retention dams or ponds. You have full flow structures. You can have full flow earthen dams. You can have chutes, weirs and toe walls, and risers added to county culverts. So here's an engineering. I just took a few pages from an engineering plan set. This structure happens to be on a fence line between 2 landowners up in Harrison County. Here's the footprint of the dam. Here's the footprint of the emergency spillway, and this is the pond limit. So basically, this structure is going to back up water and cover the head cut, which is it's kind of hard to see with this scan, but zoom in a little bit. The contours are closer here, and this whole area is going to be covered. And here's a profile of the structure, and here's the structure from a side viewpoint, and here's the gully bottom. And it's, we're trying to cover over that head cut, which is approximately in this vicinity. And then here's a more detailed image of what the structure looks like. It has a drop inlet. There's a pipe at a slight angle through the structure, and then there's the outlet. And all this is earthen dam. So these dams or ponds are often the best fix for sites needing a significant amount of grade control, because the pipe size is decreased by having more storage, more water storage above the structure. So they're really good for structures that need more than 10 feet of grade, have greater than 50 acres of drainage, and nick point or classic gullies. A full flow structure it is a structure that doesn't store water upstream of the dam, and the the water flows into the structure and through the pipe and out, and all the time. It's called a full flow because it's the water flows through. There's no storage. It's a fairly simple design and construction, and it it can be used if there's no hill to tie into. For example, you're on fairly flat ground, so this works really well for cutbacks, cutback gullies. But the drainage area can be a problem. If the drainage area gets too large, the pipe size will be greater and it costs more. Another option is like a rock or a chute or weir structure. And so this one shows a chute. Here's this dotted line is the stream bottom, and there's a nick point right here. And basically we're gonna create a grouted riprap mat of rock that the water is going to flow through. And so here's some photos of these kinds of projects. Again, it's a pretty simple design, but it's often used when the drainage area is too big for a full flow structure. And then a sheet pile weir or toe wall structure are fairly easy for contractors to construct, but because there's metal involved, more metal than with a pipe, typically they're not always the most cost-effective design, but they are really good at controlling small drops in grade. And finally, you can add a riser to a county road culvert to stop a gully on the upstream side of a road. And normally the counties are more than willing to do this. And this will work best for like the classic gully. And so that's the end of my presentation. So I guess we'll take questions later, unless someone has a burning question they want to ask now. So Terry, you want to take it from here?
Yeah, I can, John. Hi, I'm Terry Gleaves. If you didn't know, District Conservationist in East Pot. John had asked me to talk about cost share. I think a lot of you on here are NRCS. But we're talking about grade staves mainly. So equip and RCPP. Can you hear me okay, John? Okay. All right. All right. So anyway, RCPP, West Nish RCPP started last year, and Golden Hills, which John is part of, was the lead partner on that. And we targeted Grade Staves as one of our main practices. We wanted to be able to fund those and stream banks on the West Nish. So with the cost share, the Grade Staves actually, I think there's maybe 17 different scenarios depending on the type of structure, which John did a great job of showing you the different types. And the reasoning is because of the different types and size, they all will be a little different cost. So with the scenarios, for example, pipe drops are real popular around here. They basically have it split from less than or greater than 1,000 cubic cubic yards in the structure. And then there's a formula with the pipe to determine your cost share, but it's anywhere from 15 to 23 bucks a square foot based on that pipe size for the drainage. So it's very good cost share. It's designed to be around 75%. Our cost share rates are regionalized, so some of them hit pretty well, others not as much, maybe down to 60%. But it is the main form we have for these bigger structures. It takes some planning, so you have to go through maybe a year of planning, and then you need to get engineering to develop design to be able to come up with a solid estimate. Like you said, full flows, the chutes, the sheet piling, all those things can be cost shared through EQIP or RCPP, depending on what they are. Now, for you not familiar with our federal funding, there is a ranking process, and you're ranked in those pools on your projects against everybody in the state on those same types. So it's not 100%. There's just so much money in each pool that they can fund so many projects. I also wanted to touch on IDLE's state cost share as a 512 program. There's a very good program for Grade Stabes, and it's mainly for the Nishnabotna watershed. There are some parameters that they want, at least 40 acres of drainage. They like to have terrace with tile drainage into these structures, outletted into them, and the majority of the upland needs to be crop ground. So the way they do that, the first $7,500 is the landowners, and then they will pick up the rest of the project. So on all this cost share, besides the planning, I think the biggest limiting factor is the engineering, which takes time. And NRCS does the best they can. They prioritize these federal projects to get done, but sometimes that's an issue. With RCPP, we actually hired private engineering to help us with our structures, to help get them done on a timely schedule, because RCPP keeps a pretty tight budget on the money, and it expects you to do the project when it is planned out in the contract. Otherwise, unless there's some questions, that's the main points on the cost share for the Grade Stabes. Anything else you can think of, John?
No, not really. Brian, do you have any comments on engineering? Maybe pitfalls that people are going to encounter, like with the permitting process?
I would agree with both Terry and John that engineering a lot of times is kind of an obstacle. NRCS does not have a lot of technicians and engineers to do a lot of the workload that is being hit at us right now. So a lot of these structures do require some permitting with DNR and the Corps of Engineers. I think most people know that some of the larger dams require storage permits and construction permits. That's never changed in the last 30 some years. But back in October of 21, Iowa code did change. And what Iowa code classifies as a NID dam, a National Inventory of Dams, it's a threshold of overall height of 25 feet with a storage at top of dam at 15 acre feet of storage, falls into that threshold of an NID dam. And Iowa code says NID dams are permitted. So prior to October of 21, not all these NID NID dams required storage permits or construction permits, but they do now. And it's Iowa code. We can't do anything about it. So a lot of times there is some different design criteria that go into permitted dams than what might have been slightly smaller design type structures. So Corps of Engineers has recently kind of got more and more involved, or we've paid attention more and more to the Corps of Engineers on some of their permitting. Corps of Engineers, more or less, is the enforcement agency to EPA, and they are a little more stickler on what we can and cannot put a dam on. If there is running water year-round, they classify that as a perennial stream, and we're only able to more or less disturb up to 300 feet of stream length. If we're impacting greater than 300 feet of stream length, it requires stream mitigation. And stream mitigation is a whole other topic in itself. I don't think we need to get into stream mitigation on this call, but stream mitigation, in short, will probably far exceed the cost of the project itself. So stream mitigation usually kills some of these grade control structures. John, Terry, anything we need to get more specific on?
Think so. I guess one reason why I was interested in doing this presentation today is because, you know, we used to do these kind of grade control structures with landowners all the time, you know, probably before 2010, let's say. And then since 2010, we've just been doing a lot less of them, even though we have the money to still do them. And I think some of that might just be the fact that maybe people aren't as familiar with them anymore. So I just wanted to make people aware of the options that are out there, because I know there are tons of gullies still out there, and people, landowners have concerns when you have a gully eaten into their land, and it's especially if it's going to create a crossing or an access hazard. So that's kind of where I was coming from today. And Terry, you got anything?
Yeah, the only other thing I could think of is, if you're a landowner and you're unsure, well, go to your NRCS office and have somebody come out and look, and they can give you ideas, and they can give you an idea of cost, not only with what type of structure is needed, but the cost involved and the amount of cost share you could be eligible with. If you're an NRCS employee, and if you see areas that you could fix with a structure, don't be scared to say something to the landowners. Explain the cost share and explain how you could save, could be acres of his farm with some of these that could be saved. I know through my career, sometimes it's difficult when the money gets rather large, and it's never going to get any cheaper. But if we have 75% cost share rates, why, that's about as good as it's going to get. So sometimes it's worth it just to hit a guy up about something like that and get a project going.
Yeah, and to go along with that, Terry, you guys, especially if you're NRCS employees, you guys have access to, hillshade and contour data, and you could create a map like this and just go through. If you wanted to do a watershed analysis on your own, you can go through and find where the erosion is, and go talk to those landowners. That's what we did with the Silver Creek project, and that's what we did with the Wabaunsee Creek project. You know, if you guys have questions about how to do that analysis, you know, I'd be more than willing to help you out. But I guess at this point, you know, what kind of questions do people have? Hopefully there are some. And no question is too small.
Free to unmute yourself if you want. Otherwise, you can type it in the chat and I can relay to them.
I would figure if there aren't questions, either everyone was really bored by it, or I just did such a good job that no one has.
You did do a good job, John.
Oh, well,
Okay,
I'm
we have one question in the
fascinated.
chat.
I'm fascinated, you know, when you talk about when they straightened it back in the day. Can you imagine what our landscape would be like now if they wouldn't have straightened all those streams?
yep. And you know, if they were coming from Ohio or Indiana, Illinois, as they moved across the United States, you know, straightening the stream wasn't a big deal in those areas because they got so much till, you know, glacial till. It's been packed by a glacier. It's really tough stuff. Loess is not. It's wind blown. It's just laying there. It hasn't been pressed or compressed or anything, you know, so it's really erodible. You said there was a question, Lance? Oh, I can't hear you, Lance.
Oh,
There you go.
wait. Can you hear me?
Now I can.
Okay. Do you see issues with grouted riprap being undermined, or is it pretty stable in less?
Um, so with all of these structures, you have to look at the whole stream system. If you have a grouted riprap structure, um, you don't want to put that in an area where you don't know what's happening downstream, because if there's erosion between um, the outlet of your structure and whatever grade control downstream, then that's going to hit your outlet of your grouted riprap chute, and eventually you're going to have erosion and you're going to have a drop off, and then it's going to create a giant scour hole. But it won't eat through it as fast as it would if it was less, but it's still going to cause a heck of a problem. And if you ever do have to fix it, it's going to cost a lot of money. So you definitely want to be aware of what's going on downstream, and so you can either do a survey. Sometimes you can even get by with like a desktop survey, you know, just turn on your contours and see if there's any big contour, um, close contours downstream. You can walk it. You can, if you don't know and you got some money for it, you can survey it. But if you can see a graded, or if you can see a grade control structure downstream, and you know what slope you have between there, and it's not a unstable slope, then that's when you can definitely use that structure. So that kind of structure. So in these examples that I showed here, this structure is in, I think this is in Adair County, and the West Fork of the Middle Nottoway River is just downstream, and there's Weir, you know, maybe a mile downstream. And so because of the short distance to the stream, and we knew the slope in the channel, then we knew that we could put one here. This one is right along the East Boyer in Crawford County, and there's a structure on the other side of the bridge. This one is also in Crawford County. I don't remember this one, and this one's in Shelby. but I don't remember the situation with this one either. But yes, you definitely want to know what's going on downstream so you don't get erosion hitting the outlet.
Okay, another question. Does the NRCS partner with city/county to protect roads even if the adjacent gully is on private land, or would cost share all be with the private landowner?
I've seen it both ways. Quite often, a county will want to take care of the gully if it's encroaching on their road right away, because if anything happens to that road and the road embankment starts to slough away, that destabilizes their road. They don't like that. So most counties, if the gully is close to their road, will definitely want to be involved. If the gully is, quite a ways outside the roadway, uh, the county may not want to be involved. As far as whether NRCS or state cost share is available, I would think that we would still cost share on something like that. I don't know. I don't know. We've done anything like that in Pot County, have we, Terry?
I don't think so. We have done some projects with the county though, uh, where it was going to cause road damage or infrastructure damage that we've basically took it to the structure site and then the county designed the structure and put in at their cost.
Yep. And the counties have Hungry Canyons funding. If
Yep.
they have an issue like this, they can totally um, use Hungry Canyons funding, which is 80% cost share, to do something like that.
Yeah, don't see any more questions. Anybody, feel free to unmute if you have another question.
Determine the flow rate of a stream. Um, you want to take that one, Brian?
Yeah, there's several different ways you can estimate flow rates of streams. There are some. I got a 3-ring binder behind my desk, recently reprinted, probably 10, 15 years ago, drainage area of Iowa streams. Then there are some regional equations that you can plug those drainage areas in to come up with an estimated capacity of what that stream is carrying. Another place you can go to some USGS sites online. I know, like the West Nishnabotna River, I believe there's a gauging station at or right above the town of Hamburg. Oh, I want to say there's probably something near Shenandoah, probably something, I don't know, maybe Oakland or Hancock or something. But USGS has several different gauging stations on some of the larger streams. If you get on some of the smaller streams that might be 1-2 square miles, that's where you may have to use some of these regional equations. But there's some ways of doing it. Some other just general swag type deals is you can assume some velocity, and through the Q equal VA equation, you can do a cross section of a stream, assume that the velocity is going to be, pick a number, 8, 9, 10 feet per second, figure the cross sectional area of that stream, and you can determine what the flow capacity of that stream is. So if you got something more specific, don't be afraid to reach out. But there's ways of doing it.
Yeah, and the website that Brian referred to is called Stream Stats. You type Stream Stats USGS into Google, it'll take you right there. And it's really pretty handy to use. I use it a fair amount.
just keep in mind, the accuracy of how you're estimating. If you're going to be assume a velocity, assume that your flow rate might be varied. They're not hard dead set calculations. So, but it gives you a good swag answer.
It'll get you in the ballpark.
Okay, I think that's all we got. Thanks everybody for joining, and thank you, John and Terry. Feel free to go to the RCPP website and reach out if you want to learn more, and we can connect you with the field offices.
Thank you guys for setting it up.
Yep, thanks.
Thanks.
See you later.
Thanks for joining, everybody.